Hello, everyone. Today I'm going to be beginning with the first ever session on this channel. I don't even know what the channel is called, but I'm going to be beginning with the first ever session on this channel in this continuous series I'm intending to develop on physics. Namely, just high school level physics. The type of physics that's taught in A levels. And I would like to begin that with something that is not taught in A level physics, which I know sounds somewhat ironic, but trust me, once you've got a good grasp of this, you've got a good grasp of the entirety of physics, really, at the high school level at least. And that physics topic happens to be a math topic. As has been said popularly by many people, math is the language of physics. I'm going to be using abbreviations, but yeah, math is the language of physics. So, what better to do than to learn math before we learn physics? So, I'm going to be teaching you guys a bit of mathematics, all right? And here's what we're going to be learning about today. Today, I'm going to be teaching you guys a bit of basic mathematics, namely the topic of the derivative. The derivative, or as many of you may know, or actually some of you, considering this series is aimed towards AS level students, the derivative is denoted by this monstrosity, or rather, really nice looking thing. The monstrosity is this f dash of x. But we're gonna get there in a bit of time. What you need to understand is today we're gonna be learning about the derivative. Now, where do I begin? When you understand a concept, you should first of all look at, the problem the concept is trying to solve. And I feel like differentiation or the idea of the derivative is best understood in a given context. So let me give you a context. Let's imagine I've got a curve. Y is equal to x squared. Now, in IGCSE or in grade 10, whichever curriculum you follow, you've probably learned how the curve looks like. Looks like a upward facing parabola. Apologies for the terrible sketch, but here you've got an upward facing parabola, right? That is the value of, or that is rather this curve, y is equal to x squared. Now, back in elementary days, you probably learned about, you probably learned about the idea of the gradient. Well, what's the gradient of a straight line? If I had a straight line right here, I believe many of you may know this, but the gradient of a straight line is by definition a ratio. It's a ratio of the change in y over the change in x. That is what I define the gradient to be. It's a change in y over a change in x, and it's defined specifically in, this sense for a straight line. But I want to find the gradient of a curve. I want to find the gradient of y is equal to x squared. And well, what did we say? What did physicists or what did mathematicians more appropriate? I mean, technically it was Newton who was both a physicist and a mathematician, but still, what did Newton say? Or what did Leibniz say? Uh, okay, I'm not going to get into that. But what did either of the two say? They said, all right, look, if I've got a curve, the gradient, I mean, I can't just calculate a gradient of a straight line, can I? It's not just delta y over delta x. It's not a straight line anymore. So what they said is, the gradient is actually the gradient to the tangent of the curve at that point, which means that if this isn't supposed to be a gap, by the way. So the gradient at this point is the gradient of this tangent. And I'm pretty sure you guys have heard of that, right? You guys would have probably understood this concept back in the day. By back in the day, I mean like a year ago. But you've probably understood about this concept. You've probably learned about this. You've learned that, well, I'll draw a tangent, I'll sketch a tangent, and then I'll calculate the gradient of this tangent line using delta y divided by delta x. But that's the thing. Mathematicians and physicists, we don't want to keep on doing this. I don't want to continuously sketch x squared and then not even sketch. I need to draw it accurately. And then I need to draw the line. And then I need to take the ratio delta y over delta x. We're not people who like to draw curves. We're not people who even experience curves. Okay, that's probably a bit out of context. But essentially, what I'm asking you to do is I'm asking you to develop a method to find this gradient at any point. The gradient is varying, if you'll see. So in this case, the gradient depends on x. That is, if I'm at x is equal to 3, let's say my gradient is 5. And if I'm at x equal to 7, let's say my gradient is 18, right? My gradient is varying now. It's not a straight line which had a constant gradient. And what I want to find is I want to say, hey, I am currently at, let's say, x is equal to 8. And without having to, draw this entire curve and draw that line and take the ratios, I just directly want an expression for the gradient at x equal to 8. What is the gradient? And that, my friends, is the answer that differentiation answers, or rather, the answer that differentiation provides. So, what differentiation tends to do is, I tend to zoom a lot into the curve, all right? Like if I imagine a small segment along the curve, imagine this. I've got a small segment of the curve. It's like a very, very, very tiny piece in this entire large graph. I've got a very tiny segment of curve, all right? So this tiny segment of curve, what are the coordinates of its endpoints? So this I am going to tell you, right? Let's say I have a point right here, and this has coordinate x. So what's its y coordinate? X squared, right? Right, that is true. And if I go forward a distance delta x, just like we were doing with straight lines, what are this point's coordinates? Well, I've gone forward a distance delta x. So my new x coordinate is x plus delta x. All right, that's all right. I mean, I've gone forward. That's what delta x means. What about delta y? What's the change in y? Or what rather is the new y coordinate? That's interesting. What's the y coordinate? Think about it. I've marked it here. We've got an equation that maps an x coordinate to a y coordinate. So my x plus delta x right here, which is the x coordinate, can be put into this y is equal to x squared equation and give me x plus delta x, the whole thing squared, as the y coordinate. All right. So right here, what I've got is I've got 2 points. And well, in calculus or in differentiation, what I want to do is I want to do one thing. If I want the gradient of a tangent, I need to zoom in a lot into the curve. I want this delta x that's right here, because as delta x shrinks, this curved part approaches the tangent. That is, as delta x shrinks, if I imagine this is suppose my curve. Let's say this point is x, this point is x plus delta x, right? Imagine, as I shrink delta x, this point gets closer and closer and closer until eventually the points are so close, I can consider them a tangent. Visualize this. I am shrinking delta x. I'm getting my point closer and closer to my previous point. And once they're close enough, I can say, well, approximately, that's a straight line. In mathematics, what we say is, I take a limit as delta x approaches 0. Want to see what happens as this change in x gets what we call infinitesimally small. So what will my gradient be? My gradient, m, is equal to x plus delta x, the whole thing squared, minus x squared divided by delta x. Now this is just a bit of algebra right here. This is x squared plus 2x delta x plus delta x, the whole thing squared. And I'm taking away x squared. That's minus x squared. So these guys cancel each other out. And I'm dividing out by delta x. So a delta x cancels itself out. Or essentially what I get is that the gradient is equal to 2x plus delta x. That's the gradient of this small segment. And then when I say, hey, I'm taking the limit As delta x gets close to 0, it becomes infinitesimally small. Well, this delta x part gets negligible and my gradient is officially 2x. Well, great. So I have what we can call a gradient function. dy, sorry, I'm not going to get there. But the gradient is equal to 2x is equal to delta y by delta x. However, I'm saying, hey, this delta x is really small, this delta y is really small. So we denote the deltas instead by small d. So delta y by delta x becomes dy by dx as this delta x term approaches 0. So what have I done essentially? I've said, hey, y is equal to x squared. For this curve, its derivative dy by dx is 2x, right? The derivative of this curve is 2x. Now, what that means is, let's answer the original problem. What's the gradient at x equal to 8? At x equal to 8, what is the gradient? And that, my friends, is now answerable. I don't have to sketch a curve. I don't have to sketch x squared and then I need to draw that line and all of that. All I need to do is say, hey, x is equal to 8. All right then, what's 2 times 8? Well, that's 16, and that's the gradient. This is the powerful tool of differentiation. And I'm pretty sure I've gone overboard for the session time, but I hope you all have comprehended this concept really well. And I hope that I can show you guys some derivations of a few more complicated functions that are differentiated, such as sine x, cos x, natural logarithms, implicit differentiation, parametric differentiation. There is so much to this technique, or there is rather so much to this field. So I'm going to leave you guys right here. Thanks for watching.